Okay, last class we tried to review the importance of permanent magnet machines and how the magnet development have taken place in terms of the energy density and how it can we can do some magnetic calculations. If you look at the BH curve of the magnet material, there is this second quadrant where it operates, and the intersection of the load curve with the BH curve will give you the operating point of B and H. So, there is one point where the H is 0 and B is BR called remnant flux density, other point where you do not have any flux at all and you have a coercivity, that is minus Hc. Okay. So, B and H inside the magnetic decide what you connect externally, okay. Just like you have a battery where the current voltage are decided. Okay. Now, today we will in this lecture we will take up the aspect of a brushless DC drive, okay. And brushless because it does not have a commutator or brush arrangement, DC because supply is DC. Okay. The DC can come out of AC, that is but it is a regulated DC. One can think of a battery also. Now, these are all called square wave permanent magnet machine. A DC machine does not require a sine wave. Typically, a DC machine will have a trapezoidal B produced by the field winding, is not it. So, you can even have a square wave, it is all the original laws of force, Lorentz or BLV, BIL laws. So, if there is a uniform flux density also, if the current carrying conductor is there, that experiences a force which is BIL. Okay. Now, this way it is called even it does not require to have a square wave, because a battery can provide you even a fixed current into the windings. You do not, battery does not have to, DC source does not have to give you any type of a rectified current. Okay. Okay. Now, we have seen the two configurations here. This is the brushless. Brushless arrangement, and this is with brushes. Right. What is the difference between the two configurations? So, magnet is in rotor here, and here the magnet is in the stator here, fitted to this way, and the windings, here are the windings, here in the stator here, and here it is in the rotor. Okay. And you have to switch the DC. Here also you switch the DC, here also you switch the DC, and here you switch it through commutator and brush, here you have to switch it through a converter. Okay. So, the stator structure is similar to a polyphase induction motor. You can have a 3-phase winding, you can have a stator structure like that. Okay. And function of the magnet is same in both, relative motion. Only thing, one time the magnet is stationary, another time the magnet is rotating. In both cases, air gap flux is fixed by magnet, right. Air gap flux is decided by the magnet, but in one side that flux wave is rotating with the magnet, another time it is flux wave is stationary with the magnet. Okay. And they may be little affected by the armature current. Armature current may to some extent do a reaction called armature reaction. Okay, it will distort the magnet. So, that why you go for brushless is the problem of removal of brushes and more cross sectional area is available for power or armature winding in configuration where rotor is inside the stator. So, there is more because if the rotor is inside you have a less space for the copper, if your rotor is outside, if the winding is inside there is less space for the copper, if winding is outside there is more space for the copper because you have a larger body to handle the windings, is not it. External one will have larger space in the slots, no, smaller one will be there. So, absence of commutator and brush gear reduces the motor longevity. Okay, commutators are subject to fairly restrictive limits on peripheral speed, etc. If you have a commutator, it can't run at very high speed, and there are some of the problems are there. Then what are the problems are you need to have shaft position sensing. See, if you want to have brushless machine commutator, then the rotor must be, you have to position the rotor. So, you must know at what instant of time you have to pass a current in the stator winding, that will depend upon the rotor position. So, increased complexity of you require a completely electronic controller. So, brushless motor is not necessarily less expensive to manufacture than the, so configuration, so cost is a feature. Now, can you compare a brushless DC motor with induction motor? Okay. In the same frame and same cooling, the brushless PM motor will have a better efficiency because you do not have a war supply system. See, the point is in the induction motor the current that is drawn will have to supply both active power and reactive power. So, here no current to be drawn to provide a reactive power because the flux is always permanently provided by the magnet. Reactive power is what? It is only to magnetize the machine. So, that component of current which may be many times 30% also, even in no load current may be even 20 to 30% rated current, that is absent. So, it can be very efficient because that light score or losses are not there, and the power factor and greater power output, okay, difference may be even 20 to 30 for the same frame. If you get x kilowatt in an induction motor, you may get about 1.2 x in the case of permanent magnet machines for the same frame. So, power electronic converter required with brushless motor is similar in topology with PWM inverters. So, as a converter technology there is not too much difference, converters are almost similar, basically DC to AC, okay, you switch. Okay, now let us take a configuration like this, magnetic circuit analysis. Okay, this is the magnet here, let us say this is north pole and south pole. What will it do? It will pass a flux flowing like this, isn't it? It will have two paths, another may go like this. So, whatever the flux here, this will be flux by 2, this will be flux by 2, am I right? If you have a 2 pole machine, right? It is like a pipe, goes inside and have it bends twice. Now, what will be the MMF that will be that this magnet has to supply? Where are the MMF drops? It has to take care of, if it is placed here, there is certain MMF drop here in the back of iron, back of the magnet, the iron portion. So, it has to pass through the slot here, it has to pass through the end of the core, and it has to pass through this slot here. Okay. If you look at each of these, so it has to supply for the, when the flux is flowing through, there is MMF drop H dot dl, and that whole MMF has to be supplied by the magnet, isn't it? Complete MMF must be supplied by the magnet. Okay. Now, if it is a smooth road, your petrol consumption is less because MMF drop is less, isn't it? But if it is potholes are there, and so on, you will spend more petrol, isn't it? Okay, that is what it is. Okay. If you travel in a crowded place like Chandni Chowk or something, you will spend more petrol, or if you are driving in a highway, you will have less fuel consumption. So, that is what it is. So, it depends upon what route it will follow. the magnet. Okay. So, the cross section of 2 pole is a 2 pole magnet. See, now if you open circuit means there is no stator current. Supposing it is considered, let us say the stator is not carrying any current. So, it is not opposing any of the flux. Okay. So, with the stator open circuit, the demagnetization curve, supposing this is the demagnetization curve. Okay. This is the demagnetization curve which is from here. This is Br, this is minus mu naught Hc, this point. Okay. Now, this will be the load line. So, this will be the operating point. Okay. This is the operating point. Okay. Now, in open circuit, say Bt is 0.8 Tesla and Bc is 406 kiloampere per meter. Okay. I mean, this is the Hc and this is it. Okay. And this slope is the permeance coefficient of the load line. That means, this is like a load. So, it will produce a B here and it will have a minus H here at this point, is not it, intersection point, and this product of B and H will give you energy. Okay. So, axial length of both stator and rotor is about 50 millimeter. This is one of the machine, okay, rare earth magnet on the rotor. Okay. Now, you can write an analogous electrical circuit for the same magnet. So, you are and this is a Norton equivalent. Okay. Norton equivalent is you have a current source type of thing. So, you have a phi r. Okay. And you have a permeance here. Okay. This current and this is the magnet. This is the circuit of the magnet and with phi m is the flux density. So, phi m is whatever internal flux minus there will be certain its own permeance, magnet permeance, okay, it will take, and this is the okay. This is the magnet flux. I think I will show it here. Okay, phi m here, and then it has okay, I think it is another permeance here PR. Okay. This is the rotor shaft and that will take away something. This is the phi g. This is what goes to the gap. So, what it is like a Norton equivalent, certain flux the magnet is producing and it certain flux it internally is fringing, and then certain flux is taken by the rotor circuit, okay, because there is a rotor permeance also, okay, and then there is this okay, this is the reluctance of the gap Rg, okay, and this phi g is split into two portions, here phi g by 2 and here phi g by 2. This is the, and it goes through the stator yoke here, right. So, it is a magnetic circuit you can represent which will decide how much air gap flux will be there, because that is decided by the relevant reluctances etc. Okay. So, each magnet is represented by Norton equivalent circuit of a flux generator. It is generator in parallel with an internal leakage impedance. Okay. Now, phi r is Br into the area, you see magnet area. Okay. So, whatever was the flux density in the magnet into the area of the magnet will give you the flux in the magnet phi r. Okay. And there is this permeance P m naught which is here. P m naught, okay, which is mu naught into mu recoil A m by L m. This is the permeance. Okay. So, internal leakage impedance okay, the remaining permeance in the magnetic circuit is rotor leakage permeance. So, certain flux leaks through the rotor, okay, that is let us say P r 1. Modified magnetic internal permeance is given by P m is P m naught plus P r 1 which is P m naught into 1 plus the constant. I think there is a where it is P m naught into 1 plus this is small p r. Okay. Now, with magnet arc of 120 degrees, there is the area of the magnet 3 by 2 pi into r 1, you know, I think this is geometrical thing you can find out. How much is the area of the magnet into the length, length is axial length. So, most of the flux crosses the air gap via the air gap reluctance. So, there is air gap reluctance is G dash by mu naught A g. What is G dash? Is the air gap length and which is corrected for see G dash will be some constant times G, where G is the actual gap length, but because you are putting slotting is there, you know, because there is some fringing. So, you normally increase this to G dash by a product called a Carter's coefficient, and Ag is a air gap area for the opposing the flux, okay, that is the flux area per pole. Okay. Okay, area, this is the gap area and we are taken care of this fringing also like this, not the area which is facing the flux. Okay. This is the permeance, internal permeance P m, which is the P m naught plus P r 1, and this will be the gap B, that is the flux density at the gap, which is given is a product of B r into, these are some derivations are there as, okay. The C phi is area A m by A g, etc. Okay. This is just a simplification of those equations. Okay. So, we have the magnet flux B m is given by as a function of the remnant flux B r, okay, 1 plus P r, this is basically solving that circuit, okay, and minus H m, that is the magnet intensity inside the magnet is B r minus B m into mu naught into mu recoil amperes per meter. Okay, this is what is known as the permeance coefficient, which is mu recoil into 1 plus P r 1 R j over P m naught R j. I think these are all derived from the circuit. I wish we had time to do that, but I think I would request you to read out this. Okay. Now, this is the air gap flux density in open circuit. How will the air gap with theta will vary? So, typically it may have a sort of a approximate to a square wave. So, this is obviously it is spreading through 120 degrees, okay, with a peak at this case 0.53 Tesla. Okay. If this is the nature, let us look at what will be the torque developed in such machines. Okay. Now, simple and resembles to the DC commutator motor, a simple concept machine is okay. Let us take a 2 pole magnet have 180 degrees pole arc. Say pole arc can be 180 degrees or less. Okay. So, air gap flux waveform is ideally a square wave, air gap flux is a square wave, then you switch the windings at a appropriate time, so that it will produce the maximum torque and produce the required voltage. Okay. Okay, I think this is a little difficult picture. Let me see if we can try to understand it. So, we have the stator with 2 coils, okay, A1, A2, and of course, this one is other side A2, A1, okay. There are 2 coils, and magnet is, it is taken a 180 degrees magnet. North pole is spread through 180 degrees, south pole is spread through 180 degrees, and that is rotating. Okay. So, what you are trying to say is B theta will be a square wave this is 180 degrees, okay, 0 to 360, okay, this is theta, right, this is the B wave. I hope you have no problem in pick understand. And what will be the flux linkage? See, flux linkage of coil 1 this is coil 1, okay. Flux linkage of say psi 1, right, and similarly you will have flux linkage of coil 2 which may be shifted by 30 degrees. Say this angle is 30 degrees, the angle between the two 30 degrees. So, the flux linkage again it will be shifted by 30 degrees. This is psi 2, okay. Flux linkage as it as a rotor what is moving here, rotor is moving, okay, and flux density is square. So, flux linkage will not be square, is integral of that, is not it. Flux, what is the flux which will be linking? So, obviously when it is, when this coil comes exactly at 90 degrees, it will have one flux linkage. So, after quadrature it will be 0, 0 to, okay. So, here there is a 0 flux linkage, then after it is a maximum flux linkage, okay. Now, what will be the voltage induced in them? It is rotate, after all that flux linkage, what will be nature of voltage induced? Will it So, this from the one it will again be a triangular wave of flux linkage will lead right to this is EA1, okay, is not it? I am not telling very complicated things, I hope, okay. And what will be the second one? Flux voltage induced in the other winding, it will be shifted by 30 degrees. But this angle is 30 degrees, okay, right. Now, if you are connected in series, the voltage is, if there are two coils EA1 and 2, you connect them in series, the EA1, EA2, then what will happen? This will be okay. So, oh sorry, right. So, this will be EA1 plus EA2. So, that is somewhere here. Okay. Now, you have to switch the respective currents from the source. Okay. Now, this is IA. Okay. And this is IB. Okay. I think there is a, so each one, let me see if I can, IB and this is IC. Okay. Now, there are switches. So, after all, what the whole purpose is, there are 3 windings, depending upon, let us say ABC, and there is a source and this has to be switched. Okay. And what type of switches you have, in fact, I hope you know what is the inverter type. So, you have a right, where do you connect these points? This is the DC source, okay, VDC, right. So, you connect them, okay, isn't it? So, you have a, and these are all devices, in fact, this each of these switches are typically the devices which are like these switches, and that will have a freewheeling diodes. This is each of these switches. Okay. Now, that means you know when do you pass a current IA, when do you pass a current IB, and when do you pass a current IC through these switches. Okay. So, that is what we have mentioned, that will be corresponding to EA, you know. So, you have EA and IA must be such that you have maximum power, that is possible. Okay. You do not have 0 power, EA, IA must be maximum. Okay. Right. Okay. So, if you have a stator as 12 slot and 3 phase winding, what do you mean 12 slot and 3 phase winding? How many slots available for one phase? 4 slots. So, we have already seen 4 slots, A phase has 4 slots with 2 coils spread at 30 degrees. Okay. Then similarly another will be B phase and C phase will occupy the remaining space in the periphery of the stator. Okay. So, there are 2 slots per pole per phase. Okay. Each phase winding consists of 2 adjacent full pitch coils of N1 turns each whose axes are displayed by 30 degrees. Okay. The angles between them they are 30 degrees. So, consider psi 1 is the of the coil A1, okay, you call it as A1 A1 as rotor rotates and maximum positive flux linkage occurs at 180 degrees. Okay. By integrating you know what is the psi 1 max will be N1 into Bg into pi R1. Okay. Bg is the air gap flux density. Okay. We have seen what is this Bg. Okay. So, variation with theta 0 to 180 is this is psi 1 theta will be a linear function of psi 1 max. Okay, it is just a linear function because it is a straight line, a triangular wave. Okay. So, E to E1 will be minus d lambda by dt, I mean again in the way it is connected. So, it will be minus omega d lambda 1 by d theta, right. It's so, therefore, you know what is the voltage will be twice N1 Bg L R1 omega, so much of volts. This is the voltage induced per coil. In terms of speed, in terms of length R1 Bg into number of N1 is the number of turns in the coil. Okay. Right. So, EMF induced in the second coil of A is identical, but then shifted by 30 degrees. So, 2 coils are connected in series, the total phase voltage is sum of 2 separate coil voltages. So, E will be that twice, because you can add it up, you know, this is the voltage of the. So, we know what is the voltage induced in the coil. Okay. And power is twice E into I, which is omega into torque developed. See, because if you say neglect all losses, so torque will be 4 times N phase Bg L R1 I into Nm, because during any 180 degrees interval of phase current, the instantaneous power being converted from electrical to mechanical, because there is a block of 120 degrees, is not it, during when E is there. So, this is the power that will be developed and this is the torque. So, E is k phi omega and T is k phi I. I think this will be typical to any DC machine. I is the current that is pumped into the windings through the converter, through the through the battery source or the DC source. Okay. So, if that is the current I, that is the peak value. So, we have K is 4 NF, N phase and phi is the Bg R1 pi L. So, you know this is the flux per pole and this is a constant. So, you have K phi omega is the voltage and K phi I is the torque. So, if the converter is supplied from an ideal DC source of voltage V, so at any instant you can see that V is E plus Ri, is not it. R is the resistance of that circuit of each phase. V is our DC source and E is what is induced voltage. Okay. So, you can sort, so R is sum of the 2 phase resistances in series and E is the sum of the 2 phase voltages in series. So, this equation is exactly same as that of a DC motor. DC motor with commutator, you have this one. So, with so much of jugglery we have come to the same thing, but only the switching is the main issue here. And so, you have a the voltage drop across two converter switches in series are omitted, because switches also may have a drop, okay, but they correspond exactly to the two brushed voltage drops in series in commutator. In commutator machine the brushes also there is a drop, here the same thing is handled by the switches, because there will be a voltage drop across the switches, right. So, that is you can take care of. Right. Now, DC terminal voltage, EMF and torque equations, the torque speed characteristics, what will be the speed will be no load speed into 1 minus T by T naught. So, you are familiar with this, what will be the speed versus torque. So, it will just follow this curve, this is omega naught and this is the slope, okay. So, at any torque and what is T naught is the what is T naught is K phi I naught, the stall torque. If you go to, after all you can always write it as a, typically you may know that you can have this curve shunt characteristics, this is omega naught, this is T naught, okay, this is omega and T, right. So, you can write this equation. So, no load speed of this is V by K phi and the stall torque is K phi I naught, where this is the stall current. That means you block it and that is the current it will draw at the same voltage. So, stall torque is the torque when the motor is stalled, that is at 0 speed, and the stall current is given by, when it is I naught, what is the blocked current is voltage by resistance, okay. Now, the torque speed characteristic of a brushless DC machine, you can ideal one you can plot. So, the torque speed characteristic will be you can have a, this is chopping control, you can have you can have different family of characteristics here, right. So, this can be a continuous stall torque at this point, okay, and this is the stall torque and this is the omega naught, okay, no load speed. So, as the speed, what is your purpose? Your purpose is to produce the same torque at a variable speed, okay. You can have a control speed and normally you follow a constant torque operation and a constant power operation. Sometimes what happens is you can control it by chopping, that means I hope in DC machine there is a voltage control and there is a flux control, is not it, okay. And in this case of course you have a magnet, you can't have a flux control, okay. So, you have a angle control in terms of the in the converter itself, okay. So, okay. Now, if the phase resistance is small, then the characteristic is similar to that of a shunt machine. The speed is essentially controlled by the voltage V. So, what you do is if you want to control the speed, only way is to control the voltage, okay, and maybe vary it by varying the supply voltage, okay. It can even be controlled by the AC side also if it is a rectifier, okay, because DC the supply voltage. As the load torque is increased, the speed drops and the drop is directly proportional to the phase resistance and the torque. So, voltage is usually controlled by chopping or PWM. So, by chopping of the source or a pulse width modulation, you can have a voltage control, right. The continuous limit is usually what is you want the motor to always operate at constant current. So, continuous limit is usually determined by the heat transfer. Why? Because it has temperature rise is important. You want the motor not to go beyond the operating temperature, that means you want to maintain a constant current I square R. So, intermittent limit may be determined by maximum ratings of semiconductor devices, and also this device also have some switching frequencies etc. So, that is also the one which will limit the operating speed. You want this to be variable speed, and these are some of the limiting factors. Okay. So, you can get a family of torque speed characteristics by voltage control, okay, and with PWM imitation. Because you can't use if flux control is not possible, because that would mean that you better do it within the base speed. So, in fact, with what I have given you now is basically a simple principles of working of permanent magnet brushless DC motor. Of course, there has been considerable work which has taken place in this area, and with limited time it is not possible, but I think I would advise you to go through some of the good books. Say like Tom Miller has a book on permanent magnet machines, and Geiras has a good book on permanent magnet machines. Okay. And even the design of permanent magnet machines are quite involved and quite interesting, right. And there will be problem of armature reaction, inductance. After all, you know, when they are operating in such switching condition, the armature winding inductance also comes to the picture. So, what we have done is the ideal situation, but in practical cases armature inductance comes to picture, the switching power electronic circuit simulation becomes critical, okay, and high frequency switching PWM operations etc. So, you may have to learn proper simulations of these PM brushless DC machines, and what is told in today's lecture is just an introduction and to sensitize you on the issues involved, okay. And obviously, those who are interested have to go to read and learn more and go to deeper understanding of this subject. So, we close it here, and next time we will take the other permanent magnet machines, typically sine wave. Okay, thank you.